Hello there, so I'm going to talk about 938 range sum of binary search tree tonight. It's a relatively easy question because I spent quite some time spun up my GitHub repository to host all my code solutions to the Leetcode questions that I made videos about. So if you're interested, you can check the link down there in the description box. So without that, with that out of the way, let's talk about this question. So we have a reference to the root node of a binary search tree, and we want to return the sum of values of all the nodes that's in the binary search tree that's within the lower and upper bound inclusive. And the binary search tree is guaranteed to have unique values. Okay, not sure why this is here. It's not particularly helpful. Basically, the straightforward way of solving this is to traverse through all the nodes in the tree and just add those values up if they are in between this range. So a little bit improvement that we can do is to prune the search. So if we explore the nodes value, we have already processed one of the node, and then we facing the question. Do we also explore the left descendants, or do we also explore the right descendants? We can actually prune this a little bit. So if the node's value is already larger than the upper bound, we definitely don't want to go to the right descendants, because those nodes all have values larger than the current node's value. So it's going to be further towards the right. And the same reason is that if the current node's value is smaller than the lower bound, then we don't want to go to explore the left descendants for that node, because all of those nodes value are going to be smaller than this lower bound. So with that, we can just use the binary search trees property to prune the search a little bit. So potentially, we don't need to explore the whole tree, but in the worst case, if the lower bound and upper bound, if the lower bound is smaller than the smallest node's value, and the upper bound is larger than the largest node's value, this prune doesn't work. Will never be triggered. So we ended up still exploring all the nodes in this binary search tree. So in terms of time and space complexity, it's still, in the worst case, it's linear with respect to the number of nodes in this tree. So that's the pretty much the analysis of time and space complexity and stuff. So it's basically just traversal the tree with a little bit of pruning by using the binary search trees property. So with that, let's actually just code. So we're going to have a variable to keep track of the totals. That's the nodes value that we add up to get that sum. And we're going to have a stack to keep track of the nodes that we want to explore. So in the beginning, there's only the root node on the stack. So the looping condition is that while we still have nodes, we want to at least to take a look at. The first thing we do is to pop off a node. And then we try to update this total. So this is just basically checking whether the node's value is within the lower and upper bound. And then we can try to prune the tree a little bit. If I have a left child and my value is not too small, so that exploring the left still makes sense. So that's So that's this. Then we want to put this left child onto the stack. It's the similar logic for the right child. So only if that my value is smaller than the upper bound, exploring the right descendants still can make sense. Otherwise, we'll just cut off the traversal from there. Yeah, so this should be the solution code. Let's try to run it through some examples. Okay. Are there any notes on the what about this case? I guess I just handle the spatial case. I'm not sure if this question have that. Alright, so let's submit this. Okay, so whoa, I'm really slow. I need to check on the discussion forums to see what's happening. I thought I'm pretty. I think it's pretty straightforward. Yeah, but here I don't see any particular reason I'm slower than so many people. Anyway, if I find out some reasons, I'm gonna put comments down there. But as far as the video goes, this is pretty much it. So bye for now. Check on the link if you're interested in my past code.